Let's get back to our Michelson interferometer. For interference to work, you need two light beams. In the case of the double slit experiment, those light beams came from the two slits. Over here we have a single laser. That laser beam is going through a concave lens. Let's not get into that right now. And then over here it goes to what is called a 50-50 beam splitter. Basically, this is just a piece of glass with an aluminium coating. Now, what this will do, it will let 50% of the light straight through, going to a first surface mirror over here, and 50% of the light will be reflected, going to a first surface mirror over here. And those two reflected beams will go back to the 50-50 beam splitter and will be recombined going in this direction. And then over here, that will be our interference pattern. Okay, let me show you that in detail. This is a schematic of the Michelson interferometer without the concave lens. So light from the laser will go towards the 50-50 beam splitter. Now the far side of the 50-50 beam splitter, that's the side with the aluminium coating. So this will be the part that will be reflecting. 50% of the incoming light will be reflected towards this mirror over here. And then, because it's a mirror, that light will be reflected back as well. So this is 50% of the incoming light. The other 50% is transmitted and going to the other mirror. Now this 50% of the incoming light goes back and forth over here, comes again at the 50-50 beam splitter. So half of this 50% is reflected back towards the laser, and the other half of this 50%, so 25%, will be going towards the screen. Same thing is happening with the light beam going to this mirror. So this is 50% of the incoming light. Half of that will be sent back to the laser, and the other half will be going to the screen. So that's another 25% coming from your original laser beam. So in total, 50% of the incoming light beam will be going to the screen. And of this 50%, half of it went via this mirror and the other half went via that mirror. Let's align the interferometer and see it in action. So I took out the concave lens. The concave lens is here so that the small laser spot becomes like a 2 centimeter spot here on the screen later. Also, I blackened this piece of paper, and that is just because it's better visible on the camera. Now, the first part of the alignment is the laser beam going through the 50-50 beam splitter towards this mirror and back. And preferably this laser beam is sent back right at the laser pointer over there. So what I do, I will block this part of the laser beam first. So I'll block the second mirror, and then I can move this mirror just so slightly. I can rotate it, and I will try and find the spot where it actually puts the laser beam right back to the laser. Actually, this is probably okay. Now, the second part of the alignment is a little bit more difficult, but in this case, over here, I have a mount with 3 knobs on it, and this makes the alignment really easy. So here on the screen, you can see 2 dots, and those are the 2 reflected beams. So one via this mirror and one via the other mirror. And I can actually, by turning the knobs, I can align those beams. So it doesn't have to be precise, but just as good as you can. So I can, it's going in the wrong direction. So first I'll align the horizontal direction. This seems to be okay. And then I can align vertical direction. It's probably okay. So it's not that that hard to do. So let's see if it is good enough. Now, to actually see the interference pattern, we have to put the concave lens in here. So I will first put in the lens and then later try to attach it and see what happens. Oh, there is an interference pattern. Okay, so it's actually a little bit too low, but we can work with that. So it looks like it actually already works. There it is. I just blackened a bit more of the paper so that it's better visible, and maybe I can add some zooming as well. What we just witnessed was the interferometer picking up on fireworks outside. Tomorrow is New Year's Eve and people are already playing with fireworks. In case you missed it, here is it again. What happened here is that the pressure wave from the sound of the fireworks made these mirrors vibrate. And by that, the path length of the light changed a little bit. And if the path length in this arm is different than this arm, you will see the interference pattern change as well. You can actually see it changing a little bit just by my voice. An interferometer like this is very sensitive. If I only touch this mirror ever so slightly, you can immediately see that the interference pattern reacts. Now, if you look at the pattern right now, here in the middle, you can see that there is a black spot. So a black spot in the middle means that there is destructive interference. I can change that by pushing anywhere here on the plate. So if I do that, push here on the plate, very softly, you can see it can go to constructive interference in the middle. And if I push a little bit harder, it goes to destructive. And if I push even harder, it becomes constructive again. So what happens is when I push over here, and I don't push hard, just a little bit, the plate will bend a little bit. And the difference in path length in this arm and that arm will change ever so slightly. And whenever the difference in path length is only half the wavelength of the light, then the destructive interference here in the middle will change to constructive interference. And the mirror over here doesn't even have to move by that much. If this mirror only moves with a quarter of the wavelength, then the back and forth path length of the light will already change with half the wavelength. So when this mirror moves forward with only a quarter of the wavelength, then the interference pattern here in the middle will already change from destructive to constructive. So for this laser, it's a red laser of 650 nanometers, a quarter of the wavelength is only 160 nanometers. If you would use a blue laser, around 405 nanometers, we're already talking about 100 nanometers. Right? So a motion of only 100 nanometers over here for a blue laser will change a constructive interference into a destructive interference. If you put a light sensor in the middle of the interference pattern, you will be able to see the shades in between constructive and destructive interference. So you end up with a really sensitive device. Now you can build this device for less than $30 with parts from AliExpress. It is really easy to set up, really, a monkey can do it. And you can see features smaller than 100 nanometers. Awesome. Thank you for watching.